In this lesson, we're going to talk about periodic functions and how to graph periodic functions. A periodic function is a function that returns to the same value at regular intervals. And a very common type of periodic function is either a sine curve or a cos curve. So let's investigate. Suppose we wanted to graph the curve y equals sine x. Well, we could assign various values to x between 0 and 360 degrees. And we would see that we get the y values shown. And of course, we could do the same thing in radians. And if we did that and then plotted those points, we would get the curves shown here. So this first table of values right here, if we plotted those points, we would get the curve you see. Or if we let the x column be in radians, we would get the curve that you see there. Okay, those are important curves for us to remember. Now, what's interesting about this is that if we then let x have values greater than 360 degrees, the curve would perfectly reproduce itself again. And if we let x have values less than 0, the curve would perfectly reproduce itself again. And similarly in radians, the same thing would happen. Now, if we graphed the curve y equals negative sine x, we could take a table of values approach. And if we did that, we would end up with the curves shown here. Obviously, very similar to the curves for y equals sine x, just a reflection in the x-axis of those curves. Now, if we let y equal cos x, we would get the x and y values shown. And if we graph those, then these are the curves that we would get, either in degrees or radians. And if we let y equal negative cos x, similarly, we would get the same curves, except they would be reflections in the x-axis of the curves we had a moment ago. Okay, so it's important to note that these curves continue on infinitely to the left and right unless the domain's restricted. And in this course, we often just graph one cycle or maybe two cycles of each curve for simplicity, but you should note that the curves are infinitely wide in each horizontal direction, always following the exact same pattern of going up and down the same amount over the same regularly spaced horizontal distances. Okay, now a sinusoidal curve or a sinusoidal function is a function that can be expressed with the parent function of y equals sine x or y equals cos x. Now in this course, we're going to talk about curves having the form y equals a sine k x minus d plus c or y equals a cos k x minus d plus c. These are what we call sinusoidal functions, and this slideshow, this presentation, is to help you graph those. Now you might remember that this is the way that we always talk about parent functions. If y equals f of x is our parent function, we often talk about graphing functions that have the form shown. And when we do that, we can use the mapping formula. So long as xy is a point on the curve y equals f of x, we know that the x over k plus d and ay plus c will be points on the transformed function. So logically, you might be saying, hey, let's use the same approach for this section. And you're right, it works. You can do that for this section. For the rest of this slideshow, though, we're going to take a slightly different approach, okay? Now, in order to set up that approach, I'm just going to talk about a few terms. The axis of symmetry is the horizontal line that lies halfway between the minimum and maximum point of the function. For instance, if you recall the curve y equals sine x, it looks like that. Well, the horizontal line of the x-axis is the axis of symmetry because it lies halfway between the top and bottom. Okay, for each of the parent functions that we're going to talk about in this section, the x-axis will be the axis of symmetry. And now, something else to notice, after putting a y value of 0 through the mapping formula, xy maps onto x over k plus d and ay plus c, we're going to see that the new axis of symmetry will be y equals c. So like we said a moment ago, we can use the mapping formula if we want. And if we let y equal 0, in other words, the value of the axis of symmetry on the parent function, 0 will automatically, a y value of 0 will automatically map onto a y value of c, and we get our new axis of symmetry. So that's something that we can remember as we do this, do these graphs. The axis of symmetry will be y equals c. Now, since the axis of symmetry lies halfway between the maximum and minimum values of a sinusoidal function, we can also use this formula, the formula that the y value of the axis of symmetry is equal to the maximum y value plus the minimum y value over 2. You might remember our parent function of y equals sine x has a maximum y value of 1 and a minimum y value of -1. So adding 1 plus -1 and dividing by 2 would give us 0, which is the y value of the axis of symmetry of the parent. So that formula works. Now, another term you'll want to know is the amplitude of a sinusoidal function. That's the vertical distance between the maximum point of a curve and the axis of symmetry. The amplitude will always be positive because it represents a distance. The amplitude of each of our parent functions is 1. Each of those 4 functions we showed you earlier, y equals sine x, y equals negative sine x, y equals cos x, and y equals negative cos x, they all had an amplitude of 1. Now, since the value of a represents a vertical stretch factor, we can say that the amplitude will always be the absolute value of a. We say absolute value because a has to be a positive number. So we're going to remember that the amplitude is always equal to the absolute value of a. But the amplitude can also be the maximum y value minus the minimum y value of 2. Going back to our example earlier, using the sine x as our example, the maximum y value is 1. The minimum y value is -1. Well, 1 minus -1 quantity divided by 2 is 1. That is the amplitude. So we see that formula works as well. Another term we want to know is the phase shift. The phase shift represents the horizontal translation that occurred. Since the parent functions each start with an x value of 0, the phase shift will be the first x value in a cycle of the periodic function. Now, in the mapping formula, xy maps onto x over k plus d and ay plus c, we see that an x value of 0 ultimately ends up transforming to an x value of 0 over k plus d. That's the same as d. So therefore, the x value of the first point in a cycle of a sinusoidal function is equal to d, and that's the phase shift. And when we state the phase shift, we often add a direction of left or right for clarity. The period of a sinusoidal function is the horizontal length of a complete cycle. In each of the 4 functions shown, the period was 360 degrees, or 2 pi radians. You might recall when we looked at each of those, that 360 degrees is where the curve would start to repeat itself, or 2 pi radians. Now, since the k value represents a horizontal compression or stretch, and since the period can't be negative, we can actually remember these 2 formulas as well. The period will be 2 pi over the absolute value of k, or 360 degrees over the absolute value of k. Now, when we put it all together, if we're graphing a curve of the form y equals a sine of k x minus d plus c, or y equals a cos of k x minus d plus c, the following will always be true. The axis of symmetry will be y equals c every time. And it's sometimes helpful, like it says here later in this unit, to remember this, that c will be equal to the maximum y value plus the minimum y value over 2. Now, also it's important to remember the amplitude will always be the absolute value of a, and later in this unit we'll see that it's important to try and remember that that's going to equal the maximum y value minus the minimum y value, quantity divided by 2. The phase shift will be d. We'll add a direction of either left or right. If d is positive, we'll say that our phase shift was to the right. If d is negative, we'll say that the phase shift was to the left. And finally, if we're dealing in radians, we'll say the period is 2 pi over the absolute value of k. If we're dealing in degrees, we'll say that the period is 360 degrees over the absolute value of k. So let's do an example. Let's graph one cycle of the function y equals 3 sine 2x minus 90 degrees plus 1. We'll state the amplitude, axis of symmetry, period, and phase shift. Well, what we want to do, if you recall, the default way of writing this formula would be a sine of k bracket x minus d plus c. So we want to factor that 2 out, and we end up with this expression right here. Well, we can see right away our amplitude will be 3. Since we're dealing in degrees, as shown here, we can see that our period will be 360 degrees over 2. So our period will be 180 degrees. Our phase shift, since d is positive 45, because remember you change that sign inside the bracket, since d is positive 45, our phase shift will be 45 degrees to the right, and our axis of symmetry will be y equals 1. Okay, well, the first thing we're going to state, though, is that the parent function is y equals sine x. Okay, so we're going to start with one of these curves, either in degrees or radians. But like we said a minute ago, this is clearly a question where they want us to use degrees because it's stated in degrees. So we're going to use this right here as our parent function. Now, this is key. There's 5 key points to a cycle of a positive sine curve. We go from 0, 0 to 90 degrees, comma 1, to 180 degrees, comma 0, to 270 degrees, comma negative 1, to 360 degrees, comma 0. 5 key points. Something that's really, really important to get is that the vertical distance from point 1 to point 2 equals the vertical distance from point 2 to point 3. It's the same vertical distance. And not only that, but the horizontal distance from point 1 to point 2 equals the horizontal distance from point 2 to point 3. And we can go even further because the vertical distance from point 3 to point 4 is equal to the vertical distance from point 4 to point 5. Well, that's good to know. And it's that vertical distance from point 3 to point 4 and from point 4 to point 5, that's the exact same as the other 2 vertical distances we found before. We have a name for that vertical distance. That's the amplitude. So whatever the amplitude is, whatever that a value is, that's how much we want to make sure we go up or down between those 5 key points. And not only that, but this horizontal distance that we said was the same from point 1 to point 2 and from point 2 to point 3, well, it's the same from point 3 to point 4 and from point 4 to point 5. Well, that's awesome. Well, we know that the entire horizontal distance is called the period. That's something we learned earlier. Well, we're going to call the period divided by 4, in other words, that unit that's equal to the 1/4 of the period, which is equal to the horizontal distance from point 1 to point 2, and also 2 to 3, and also 3 to 4, and also from point 4 to point 5. We're going to call that an important interval. Now, this isn't really an accepted math term. It's just something that, or a key interval. That's just something that I'm going to say throughout this lesson to let you know what I'm referring to. Okay? Now, every one of these key intervals is going to have the same horizontal distance. So like we said a minute ago, that distance is the same as this distance, which is the same as this distance, which is the same as this distance. And we call that the key interval. And each of these key intervals has the same vertical displacement, as we said a minute ago, and that's equal to the amplitude. Okay, so our 5 key points, we said earlier in the lesson that we said that the first x value of the first point will be d. Okay, now when you look at a positive sine curve, we see that the first point starts on the axis of symmetry. Well, that means when we graph our transformed function, our first point needs to be on the axis of symmetry, so our first point will have a y value of c. So we already know our first point of our 5 points will be d comma c. All right, well, very good. Let's keep on going. Well, we know when we start with a positive, when our parent function is positive sign, we know that we go up to get from point 1 to point 2. Okay, well, that means our x value of our second key point will be the first x value plus a key interval, d plus a key interval, and our second y value will be the original y value, which was c, plus 1 amplitude. And we've got our second key point. Then to get to our third key point, we can see just by observation that the third key point will be back on the axis of symmetry, so it'll have a y value of c, but its x value will now be d plus 2 of these key intervals. Our fourth key point will have an x value of d plus 3 key intervals, and our fifth point will have an x value of d plus 4 key intervals, or in other words, d plus the whole period. The fourth key point will have a y value down here. It'll be the y value of the axis of symmetry minus an amplitude. And finally, the fifth key point is back on the axis of symmetry, so it has a y value of c. Okay, so all we have to do now is figure out the amplitude, the axis of symmetry, the values for d, and the period. Well, our amplitude is the absolute value of 3, okay, right here, that 3 right there, the absolute value of that gives us our amplitude. The 2 right here is helps us get our period. Our period will be 360 degrees over the absolute value of 2, so our period will be 180. Our axis of symmetry is at y equal 1. That's pretty easy. And our phase shift will be 45 degrees. Remember, change the sign from what you see here. Okay. Now, recall that we're going to take this period and divide it by 4 in order to get the key interval. So a period divided by 4 is going to be 180 degrees divided by 4, which is 45 degrees. So every one of our key intervals will be 45 degrees horizontally, and it will be 3 units vertically. Okay, and that process of dividing our key interval, our period by 4 to get the key interval is true for every one of the 4 parent functions, no matter which one we're using. Okay, so our key interval will be 45 degrees, like it says at the bottom of this slide. So if our first point is at DC, that's 45 degrees, comma 1. Our second point is D plus a key interval and C plus an amplitude. So D is 45. A key interval, as we said a minute ago, is also 45. So this is going to be a 90 degree right there. And our Y value will be the C, which is 1, plus the amplitude, which is 3. So it'll be at 90 degrees, comma 4. Now, when we add 2 key intervals, we'll be taking 45 degrees, which is our D value, and adding 2 more 45 degrees. So it will have 135 degrees, and we'll be back down our Y coordinate at a value of C. So we're going to have 135 degrees here, and our Y coordinate will be back down at C. Then when we add 3 key intervals to our D and we have C minus an amplitude, our point is 180 degrees, negative 2. And finally, when we have D plus a period and our Y coordinate is C, we're at 225 degrees, comma 1. And we can graph that curve. Okay? Now, the good news is that the process for graphing transformations of the other 3 parent sinusoidal functions is very similar. So just to refresh your memory, y equals sine x is one of our parent functions, and it looks like this. Y equals negative sine x, as shown earlier in this slideshow, is another one of our parent functions, and it looks like this. Y equals cos x, as shown earlier in this slideshow, is one of our parent functions, and it looks like that. And finally, y equals negative cos x is another one of our parent functions, and it looks like that. Okay, so that's good for us to remember. So if we have a negative sine curve, we'll see that our first point will be on the axis of symmetry, so it'll have a y value of c. And we'll see that the third and fifth points will also be on the axis of symmetry, so those third and fifth points will also have a y value of c. To get from the first point to the second point, we have to go down one amplitude, so our second point will be c minus an amplitude. But to get from the third point to the fourth point, we'll have to go up an amplitude from the axis of symmetry. So our fourth point will have a y coordinate of c plus an amplitude. Now, just like in the last one, our in every one of these situations, our 5 x values will always be the same. Our first x value will always be d. Our second one will always be d plus a key interval. Our third one will be d plus 2 key intervals. Our fourth one will be d plus 3 key intervals. And our fifth one will be d plus 4 key intervals, or in other words, d plus a period. If we have a positive cos curve, now this is a little bit different, because for a positive cos curve, we see that it's the second and fourth points that are on the axis of symmetry. So the second and fourth points have to have the y value of c. That first point, though, that's above the axis of symmetry. That's actually one amplitude above c. And that last key point, the fifth one, that's at the same y value. That's actually one amplitude above the axis of symmetry. So that's c plus an amplitude. But in between that third key point, we see that in order to get there, we have to go down from the axis of symmetry. So it's going to be c minus an amplitude. And like we said earlier, our 5 x coordinates will always be those 5, no matter what parent function we use. And finally, if we have a negative cos curve, again, our 5 key the x values of our 5 key points are given by these x values shown here. In this case, with the parent function is negative cos, we see that our second and fourth key points have a y value equal to c. Our first and fifth key points are below the axis of symmetry, and our third key point is above. So something that's good to remember before we go on into these next questions is that every single one of these, no matter what parent function you have, you will always have the same 5 points for graphing one of these cycles. Your first point will have a x value of d. Your second point will have an x value of d plus a key interval. Your third point will have x value of d plus 2 key intervals. Your fourth one will have an x value of d plus 3 key intervals. And your last one, your fifth point, will have an x value of d plus 4 key intervals, or in other words, d plus a period. And your y values there's only 3 possible y values. One of them is c, in other words, the point is on the axis of symmetry. Another one is c plus an amplitude, and another one is c minus an amplitude. Those are the only 3 possible y values. So your job becomes to place those y values here as appropriate. And you just have to go by whether you're starting on the axis of symmetry or starting above or starting below, and then use some logic and apply it to the graph. Okay, so suppose we wanted to graph one cycle of the function y equals 2 minus 5 cos 3x plus 90. First thing we do is we take that 2, we bring it to the end, we factor out the 3, and we get the expression shown at the bottom. Okay? Now, we see right away, since a is negative 5, that our amplitude's 5. Since k is 3, our period will be 120. Since D is negative 30, our phase shift will be 30 degrees to the left. And since Y is 2, that will be our axis of symmetry, Y equals 2. Now the key interval will be the period, which is 120, divided by 4. It's always the period divided by 4. So in this case, that'll be 30 degrees. So we look at the parent function for y equals negative cos x, and we see that that parent function has an initial x value of d, and then c minus an amplitude. The next x value, as in every case, is d plus 1 key interval, and then c. The third key point is d plus 2 key intervals, and then c plus an amplitude because it's above the axis of symmetry. That fourth one is at d plus 3 key intervals, and then it's at c again. And finally, that fifth point is at d plus an entire period, in other words, 4 key intervals, and we're back at c minus an amplitude. Okay, so we're going to apply that knowledge as we establish what the points are. So the first point's at the minimum, the second point's on the axis of symmetry, then the third one's on the maximum, the fourth one's on the axis of symmetry, and the fifth one's on the, sorry, this should say minimum, down here. Okay, and when we plot those, when we establish what those points are, we see that we have the d value of negative 30, the c value is 2, but we're subtracting 5, which has given us that negative 3 right there. And then in our second one, we have our original d value plus a key interval, and our y value is just the y value of the axis of symmetry, and we evaluate. And we go through the process like that. And so notice that the x values, all they're really doing is they're going from negative 30 to 0 to 30 to 60 to 90. We're just adding 30 degrees each time, which is 1/4 of the period. And our y values are pretty standard too. 2 of them are on the axis of symmetry, and then one of them is 1 amplitude above, and the other 2 are 1 amplitude below. And so once we establish what those points are, it's pretty easy to graph the curve. Okay, what if we want to graph one cycle of this function? Well, now we're in radian mode, but that's okay. All we do is we factor out the 1/2 inside the input of sine. A is negative 3, meaning the amplitude is 3. K is 1/2, which means the period's 4 pi. D is negative pi over 2, so our phase shift is pi over 2 to the left, and C is 1, so our axis of symmetry is at y equals 1. So you want to remember the key interval. Well, the key interval is always period divided by 4. 4 pi divided by 4 is simply pi. And so now we're going to take a look at the parent function. The parent function here is negative sine x. And so we see that for that parent function, our first, third, and fifth y values will all be c. Our second y value will be c minus an amplitude, and our fourth y value will be c plus an amplitude. And our x values, as always, will be d plus a key interval, d plus 2 key intervals, d plus 3 key intervals, and d plus the period. Okay? So, we can see, as in every case, these are always our 5 key points. And we just have to figure out, what order to put c minus an amplitude, and c plus an amplitude. So as stated, this goes from c to c minus an amplitude to c plus an amplitude back to c. Okay. Now the key interval, as we said, is pi. We'll call it 2 pi over 2 because we need to be adding it to negative pi over 2, so we're just using a common denominator there. And so our first point of the curve we want to graph is negative pi over 2, 1. Our next one is pi over 2, negative 2, 3 pi over 2, 1, 5 pi over 2, 4, and finally 7 pi over 2, comma 1. Okay? And all we're doing there for our x coordinates is we're just adding an extra key interval every time. And for our y values, we're starting on the axis of symmetry. We're back at the axis of symmetry for the 3rd and 5th points. But in between, we go down an amplitude, and over here, we go up an amplitude. Okay? So plotting those points gives us the curve that you see there. Now notice one thing, we're not, after we graph our 5 key points, we're not doing this. We have more class than to do that. We're trying to make sure that our curve is curvy. Okay, whoops. All right. So moving on to our last example, we want to graph one cycle of this function and state period, amplitude, phase shift, and axis of symmetry. Well, we can see our amplitude is going to be 6. Our k value is 1, which means our period is going to be 2 pi over 1, which is 2 pi. Our d value is going to be pi over 12, because that's our phase shift. And our c value is 0, because there's a plus 0 implied at the end. So there's no movement, there's no translation up or down in this function. Okay, so this is what we get. Now, since our period is 2 pi, our key interval will be 2 pi divided by 4. It's always the period divided by 4. 2 pi over 4 is the same as pi over 2. Now, when we look at the parent function of y equals cos x, we see that we have these 5 key points shown here. Remember, our 5 key points for our 5 key x coordinates will always be d, comma, d plus a key interval. Sorry, the first one will be d, the second one will be d plus a key interval, the third one will be d plus 2 key intervals, the fourth one will be d plus 3 key intervals, and the fifth one will be d plus a period. We see that our second key point is on the axis of symmetry, as is our fourth, so both of those will have y coordinates of c, but our first and fifth will be c plus an amplitude y coordinate, and our third one's y coordinate will be c minus an amplitude. Okay, and so we're able to state that this will be our the process that our curve goes through. Okay, and we plug in, as we said earlier, what the points will be. And remember, a key interval in this case is the period divided by 4, so it's pi over 2. We'll call it 6 pi over 12 because the phase shift of pi over 12 needs to be added to that. We want a common denominator. And so we have d plus a key interval, d plus 2 key intervals, d plus 3 key intervals, and d plus a period. And we start at the maximum point, which is the axis of symmetry plus an amplitude, down to the axis of symmetry, to the axis of symmetry minus an amplitude, back up to the axis of symmetry, and then back up to the axis of symmetry plus an amplitude. And when we do all that, we are able to graph our curve, and it looks like that. So hopefully that was a useful discussion for you.